Hi everyone, Becky, your science tutor here, and today we're diving into the world of metallic bonding and alloys. If you've ever wondered why metals are so strong, shiny, flexible, that's down to metallic bonding. And what we can do with metals is we can mix them together with another metal or another element, and we can produce alloys to change their properties dependent on their use. So let's break it down and see how these bonds help to shape the world around us. Okay, right, so in metallic bonding then, let's first of all just remind ourselves of where that division is on our periodic table. How we know whether we're dealing with a metal or a non-metal is we simply follow our aluminium steps. So start across at aluminium and simply draw our set of steps down your periodic table. Now metals make up the majority of the periodic table. So all of the left hand side are metals, and then we have this midsection here. I'm just sort of going to label separately as the transition metals. Okay. And when we talk about the properties of metals, we are usually referring to the transition metals. These are what I call more your typical metals, so things like copper, iron, ones that are a little bit tougher and used more in every day. When I'm thinking typical metals, we're going to talk about things like your door handles and jewellery and grates on the road and what cars are made of. Group 1 and Group 2, we know that they're quite unusual because we've studied Group 1, we know that they're quite reactive metals. So we're going to refer more to the transition metals today. That's more of our typical metals. Okay, so metallic bonding then. So as we've discussed before, let's start with that. So metallic bonding occurs between metals or in metals. We would talk about our metallic structures, and we would describe them. If you are asked to describe the structure and bonding, we would describe them as positive ions surrounded by delocalized electrons. Okay, and let's dive into that a little bit deeper so we can understand why do we have these positive ions, why are we not talking about them being atoms, why we're referring to them as ions. So if we take something really simple, so I'm going to use a group 1 element just because it has a really simple structure. So if you're just going to use lithium, just for the sake that I'm only drawing 3 electrons, just to show you what I mean by what's going on here. So if we've got lithium, we know that it's got 3 electrons and it's got 1 in that outer shell. Now we talk about it being these positive ions because if I just copy that for a moment and we just put some together. So metals are arranged in these nice neat rows, in these layers. Whoops. And if you are going to draw a diagram to support your explanation, you need to draw a minimum of 6 atoms. So I'm going to put 6 in here. Okay, and then what happens is that these electrons in the outer shell, just make that a bit narrower again, so the electrons in the outer shell, these can become delocalized and they can move through the structure. So these electrons can sort of move anywhere in the outer shells of those neighbouring atoms. So think back to our fundamentals. If we have an atom, it has 0 overall charge because it has the same number of protons and electrons. But if this electron for the moment is essentially over in another atom's electron space, shall we call it, then at that moment, if I label this number 1, it's like that atom number 1 has temporarily lost an electron. So because that electron has moved, we've lost an electron, we've now got more protons than electrons, and therefore essentially for while it's moved, it has a +1 charge. Remember, when we talk about charged particles, we refer to them as ions. So we say that they are positive ions surrounded by those delocalized electrons. Okay, now they are arranged in layers. And we're going to discuss why, or what those layers and these delocalized electrons, what they do to the properties. Because we're going to think about, well, why are they flexible? Why can we sort of change them into the shape that we want? We can hammer them into shape. They're called malleable. So why are they malleable? Why are they ductile? Why can we draw them into wires? What is it about them that makes them great conductors of electricity? We know that most wiring is made from copper. So what is it that's giving them those properties? Okay, so I think, yeah, I'm going to copy this. I'm just going to copy this slide just so I can add a few more notes to it. Okay, so I'm just going to make a couple of notes here that it's the layers. The layers can slide, and what that means is that we can change the shape of them. Okay, so that's why metals can be shaped. And the fact that they have those delocalized electrons, so it's the delocalized electrons that means that we can conduct electricity, because they can move and carry charge. Okay, so questions most typically asked, possibly for you to describe the structure and bonding, which case we would say they are positive ions surrounded by delocalized electrons. Why can metals be shaped? Because they're arranged in layers that can slide across one another. And why can they conduct electricity? Because they have delocalized electrons that can move through the structure. Now, if we want to change these properties, because metals, pure metals, tend to be quite soft, because of those layers, they easily slide and they easily change shape. And if we want them to maintain their shape, like the grates on the roads, jewellery, if you had a pure gold ring, you think about just everyday general wear, touching the desk, grabbing old door handles, you're gonna knock that ring quite a bit just day to day, and we don't want it to lose its shape. So what we would do is we would alloy it. So an alloy is a mixture of a metal and another element. It can be another metal. You will often see definitions of alloys that talk about them being a mixture of metals. Not incorrect, but it doesn't always have to be another metal. It might be carbon, for example. So iron is alloyed with carbon to produce steel, and steel is what is used in all the infrastructure in buildings, when you see just like the steel framework go up, and then scaffolding around buildings, the steel poles, etc. So alloys, we'll write down, are a mixture of a metal and another element. Okay, now what is it that makes it change its properties? Well, if we think about our normal metal, and we've got atoms that are all the same, they're all the same size, or in those nice neat rows, and they just quite easily slide across one another. However, when we have an alloy, we've got elements that have two different sizes. And because they have two different sizes, if we look at this, I'll label this diagram number 2, you can see now that we've basically disrupted those layers. They're not in those nice neat rows anymore. And so that prevents them from sliding. And so because they can't slide, it changes their properties, it makes them stronger. Okay? So questions often ask you to explain why an alloy is harder than a pure metal. And we would say as our answer that alloys contain elements of different sizes, because that's key that we've got different sizes, so we're not in these nice neat rows. Okay, now these different sizes, marking point number 2, is that it disrupts the layers. You will also see the term distorts the layers. Either is fine. And the third point that we would talk about is because we've disrupted those layers, it's not easy to slide, or they don't slide anymore. It prevents sliding. Ideas around the fact that it's now harder for those layers to slide. So when we look at some example questions in a moment or two, we'll see that sometimes questions around this are worth 2 or 3 marks. Why are alloys harder? Describe the structure of an alloy, something along those lines. You'll see those examples in a moment or two. Okay, so let's jump in then to some of the questions. So first of all, we've got magnesium. So magnesium is a pure metal, and it's shaped to make magnesium ribbon. So explain why metals can be shaped. We're just worth the 2 marks. So we're going to talk about the fact that the atoms or the ions are arranged in layers. So that is marking point 1 for identifying that they're in layers. And the second marking point comes from the idea that because they're in these layers, they can slide across one another. Okay, so your 2 key points there are layers, slide. Yeah, so your layers can slide. 2 marks. Here we've got a little bit more of an extended answer. We've got 4 marks, and it says that copper is used in electrical appliances. So what this one wants you to do is first of all describe the bonding in a metal, and then explain why that means that they can conduct electricity. So we'll start by describe. Remember we talked about these different command words. To describe is just to say, and explain is to say why it does what it does. So describe the bonding in a metal. So we've got positive ions, and we can say that they're arranged in layers. Now the layers isn't as important in this question because what it's going on to ask is about the electricity. But they are still arranged in layers, and then we need to include that they're surrounded by delocalized electrons. Okay, so that's picked up our first 2 marking points. We've got positive ions in layers, and we've got those delocalized electrons. So now we need to explain why they can conduct. This is a separate point, and explain why they can conduct. So the delocalized electrons can move through the structure and carry charge. So we've got to describe the bonding, positive ions and layers surrounded by delocalized electrons. Why can they conduct electricity? Because the delocalized electrons can move and carry the charge. Okay, simpler one then, so a shorter version of an alloy. So explain why an alloy is harder than a pure metal. Okay, so we've got metal Y. So if we didn't have anything else, it would just be those metal Y atoms, so they would be in the layers. And we've included metal X. So metal X we can see is larger than Y, and so we've got elements of different sizes, disrupt those layers and stops them from sliding. Okay, so we could say that metal X is larger because it's given us that diagram. Remember, when there's a diagram, it's there to help. Use it. Look at it. Think about what's going on. So we can say that metal X is larger. Okay, that's marking point number 1. And it stops the layers from sliding. And marking point number 2. Okay, we could have gone a little bit deeper with that answer and said that metal X is larger. This disrupts the layers, which stops the layers from sliding. But we're just at 2 marking points. So one is identifying that we've got atoms of different sizes because we said metal X is larger, and that stops the layers from sliding, which makes it harder than a pure metal. Okay. And then here we've got a 3 marker, so this is where we would need to say that extra point of that it disrupts the layers. So we've got oil rigs are used to drill for crude oil. Drill heads are made from steel, and steel is an alloy. Explain why alloys are harder than pure metals. So we'll say that alloys contain atoms of different sizes. Different sizes. Change that. This disrupts the layers. Remember, disrupts, distorts, whatever word works for you. And stops them sliding. Now remember, you're all going to answer this and you're all going to sort of regurgitate this in slightly different ways. The key points are, and whenever we're marking it's always ideas around that alloys contain atoms of different sizes. It's the different sizes. So like in this one, we didn't say metal X and metal Y are different sizes, but we've said that metal X is larger. You can see that in the diagram. So we have identified that they're of different sizes. So the first marking point is the different sized elements or different sized atoms that are in there. Second marking point is something to do with disrupting or distorting those layers. Again, whatever word just links in and works for you. And marking point number 3 is that it stops those layers sliding and therefore makes them harder than pure metals. Okay then guys, hope that has helped. Hope that's helped to understand why metals conduct electricity, why they are malleable, why we can bend them and shape them, but also how we can change their properties to make them more useful. Alright then guys, I'll see you next time.